Hi, everyone. We do indeed work together, and I need to be very careful what I say today, because just last week, MIG managed to break Amy's stuff. So now today I'm like, no, it won't happen again, I promise. It should never happen, but it did happen, so I feel bad about it. So how many people in this room have more than 1,000 servers to manage? Woo, a lot more than I thought. Okay, so you probably run into that problem where once in a while you have to search for something and you end up in parallel SSH hell or cluster SSH hell, trying to run multiple terminals or trying to run commands and looking for either a package that's installed or a file on the file system or something like that. That's a problem we've had for a while, and this is what MIG, so Mozilla Investigator, is meant to solve. So you can view, there are a few demos in here, and the slides are online, so if you want to just grab them, follow along, or whatever, you can get them at mig.ninja/LISA15. I know it's a kick-ass domain name. All right, so who am I? My name is Julien Vehent. I'm a security engineer at Mozilla. I do a lot of security tool development, architecture, risk assessment, threat modeling. So typically when a team comes in and says, we want to do this new crazy thing, what do you guys think? And we go in and we try to break it for them. I've worked a lot on SSL TLS stuff. If you've ever encountered the Mozilla server-side TLS guidelines, that's something I've worked on, and a bunch of tools for that, all sorts of, in particularly all sorts of stuff that helps the DevOps culture and doing security in a DevOps way. So not getting in the way of doing fast infrastructure, but actually helping it and writing tools that help do it. And maybe you've seen something called the Mozilla Winter of Security. It's a mentorship program we do to bring students in and help them work on security projects. That's another thing I like to work on. But most importantly, I've worked on MIG. I'm not alone. There are a number of people working on MIG. My commit ratio is inflated by the thousands of third-party dependencies I've pulled in. So that's why that looks good on GitHub, but I'm definitely not the only one working on this. There's another guy here, Dustin, who's helped us write a whole bunch of stuff too, and a few more people at Mozilla. So before we get into all of the slides explaining why we did this, let's go through a quick demo of what MIG actually is. And what this does is running on my local machine. This is a recorded demo, but it would. And it calls a MIG command line, and the file module will go look for something inside etc crondy, if I'm remembering it right, for a file that contains a particular string. And what that does is, on my local machine, it will generate an investigation, and that investigation will be distributed to all of the servers of the infrastructure. And this is running in real time. So all of the servers will then, on their local system, run the MIG agent, the file module, go look inside etc crondy, and if they find a file that actually matches that string, they will return a result. And in this demo, the server opsec1.private.phx1.mozilla.com has returned a match. And we can see that it ran in 12 seconds across 1,251 agents. So it's really fast, and that's really the main goal of MIG. You can take an operation, a search you want to do through your infrastructure, and run it, and it will be distributed to all your systems and comes back in a very, very short time. Definitely much faster than doing it with PSSH, assuming you have SSH access to all of your systems right away and you don't have to jump through hoops to reach everything. So what happened here? Maybe I can rewind this a bit. Let's see. There you go. So on my local machine, I created an action that was sent to the MIG API. The MIG API verified the signature. I will touch on that, but that's one of the strong security aspects to it. And the API will write that action inside a Postgres database. Okay. Behind the Postgres database, we have a scheduler. And the scheduler grabs that, and it will look inside the action targeting string and expand that targeting string to a list of servers we want to investigate at any given time. And each of these servers will receive its own copy of the investigation. And it's being pushed through RabbitMQ to the agents. The agents have their own copy. They will verify the signature again, make sure they don't run anything bad, and will run the investigation locally using modules, return the results back through RabbitMQ, and they get grabbed by the scheduler again. The scheduler We'll write them into the database. I slowed that down a little too much. Write them into the database, they go back through the API into the investigator, and the investigator then receives all of that JSON data back and displays it on the command line. So very quickly, you get all of the results of your entire infrastructure represented to you. So why are we doing this? There are a number of goals behind MIG. The first one is back in 2013, if you follow a little bit the security world, how many people are security, specifically security people here? All right, so a few. So you will know about this. In 2013, Vehent released the apt1 report, which is a very long and thorough analysis of this Chinese government-sponsored hacking group that has been targeting corporations in the US and Europe for years. And they wrote that extensive report explaining how apt1 operates and how they infiltrate these companies and what vectors they use. And alongside the report, they released what we call IOCs, indicators of compromise. You can think of them as antivirus signatures. They are checksums of files, byte strings, IP addresses, all sorts of things that are interesting and representative of their activity. And when the report came out, everyone realized that we need better tools to actually scan our infrastructure for that type of threat. How do we know that we have a specific IOC on a system? Well, you could deploy antiviruses on all your servers, but that's probably not going to happen. So we needed a tool to scan. And at first, we looked at doing it with tools like PSSH. Let's try to do a find command through PSSH and do a whole bunch of MD5 sum and try to grab the results. But that's really ugly, and you have to rewrite a script every time you need to run something. So we realized we need a better tool for this, and that was the prime motivation behind MIG. But it's not the only one. The other one, and that's probably where MIG is the most useful today. It's covering for the small day-to-day mistakes. And on any infrastructure, at some point, there will be someone who paste-bins a private key or a password or something, and it will leak. And suddenly, you have to rotate that password across your entire infrastructure. And the example here that happens a lot is that you put your AWS keys on GitHub, and suddenly everybody else has access to it. And Amazon will scan it and deactivate it, but if it's not an AWS key, if it's like any other API, most likely you'll get hacked before you notice it. So what we use MIG for here is that when someone realizes they've leaked some information, we need to locate where that secret is used. So we actually use MIG to scan a whole bunch of directories across infrastructure for that particular secret string and find where it's used so we can change it. It's a helper to all of our automation that we have in place to maintain the servers. And at the bottom here, you can see the command you will run to search for that particular secret in a Bodo file. The third goal is measuring security compliance. So there have been a few talks here at the conference about security compliance. But the main idea behind it is you have all of these servers and they've been configured perfectly 6 months ago. How do you know they are still perfectly configured today? Or how do you know that your automation is working correctly? And if you're doing immutable systems, then probably you want to do that kind of test in your build environment. And when you build a new system, you want to verify that everything is set correctly. So it's kind of a way of seeing unit testing, but at a security level. So security testing through MIG of your entire infrastructure in real time. And we graph that. We have various tests. So typically they are just tests on configuration variables in your files or verifying that SSH doesn't accept root password login or this sort of things. And we put that into investigation files and we run them on the infrastructure every day and we graph the results and then give that kind of pretty pie charts. So in a perfect world, you don't need MIG. In a perfect world, you have a perfect environment that's perfectly controlled and everyone is just following the same practices and you don't need MIG because you know exactly what's happening and when. But we don't live in a perfect world. And Mozilla is this interesting organization where we like to experiment a lot and fast. We have this startup mindset. I like to compare Mozilla more to an incubator than a real organization where we will let people experiment and play with things. And eventually, if it's successful, we will deploy it correctly. But for a long time, it will be in a broken state. So people experiment, they fail fast. And they will have, I think we have close to 30 or 40 AWS accounts Things are running all over the place. Heroku, Rackspace, I think we got rid of that eventually. We used to have 2 data centers. I think we have at least 1 now, but even like 15 offices. I forget the exact count. There's things all over the place. And we don't really centralize. Like, we don't tell people, you must do things this way. We give them guidelines, but eventually it's their job to do it the right way. So the bigger operational teams, like Amy's or a few other teams, they will follow operational standards, but when you have smaller teams that just want to experiment, they will kind of do things their own way. So as a result of that, this is what incident response at Mozilla looks like. It's not a haystack, it's a stack of haystacks. And when an incident happens and you realize you have to look through 4 or 5 different AWS accounts, the first thing you have to do is to try to gain access to the AWS accounts before you can even start looking onto the systems. For us, on the incident response side, it's very, very slow. So the point is, security at the perimeter, the way you will do it in a tightly controlled organization, does not work when you have stuff all over the place. And you need a system that is more distributed, that doesn't assume that you can just put an IDS at the edge of your network and filter all the traffic. MIG was built for this. It was built to be distributed across many different AWS accounts, not making any assumption on what kind of operating system we're running, what kind of distribution. It's just supposed to go there and do its thing, and whenever we need to look at something, it will be available. So a few core principles. I've worked with OpSec primarily before developing MIG, and I love the tool, but I found that it was still too centralized. There was not that distributed aspect to it. It was really hard to manage, and I ran into operational hell around 200-300 systems. When I joined Mozilla and they told me, we need to find something, I looked at OpSec, and like, there's no way we can manage that for 7,000 servers. We're just going to spend our time trying to flush the queues and reconnect the agents, and that's not going to work. So one of the core principles of MIG is that it needs to be massively distributed. It needs to be easy to just disconnect and reconnect everything, and it needs to be easy to run an investigation and have it massively distributed and come back quickly. I like to think as sysadmin and ops people as my friends. They don't always agree. But that's how I like to think about it. It makes me feel good. And so writing a tool that's simple to deploy was really important to me. And I think at that point we have MIG deployed in probably 50–60% of Mozilla. And it's been a breeze to deploy it. Okay, it's broken once, fine.
I haven't said anything.
I know, you're just looking at me weird. Twice, okay, fine, twice. Got it. In 2 years. But it's really easy to deploy, and I'll touch on that a little bit, but the way the agent is built, it's a self-contained, statically built binary, and just put it on a system. It can be built with its own configuration, or you can provision a configuration file, and it's simple. There's no dependency hell. You don't have to cater it to the to a particular distribution. It's very straightforward. Security, I'll touch on that a bit too. We wanted to make sure that losing access to the infrastructure, the servers behind MIG, the APIs, the scaler, would not actually compromise the agents and the servers that run at Mozilla, because MIG needs to run as root. And if you look at a lot of security tools, once you gain access to the servers behind the security tools, you gain access to the entire infrastructure. And that, to me, is not acceptable. You can't guarantee that your stuff is going to be secure all the time. So you can't take down the entire network when you get owned. And one other aspect to it is the privacy aspect. And that's a little trickier, but a lot of security tools will retrieve all the data from the target servers and store it in a central database. That's great, but that's not going to work for us. One day, we're going to deploy MIG on laptops of end users. And if you try to tell a Mozilla crowd that you're going to be inspecting the laptops with a security tool, you're not making it out of the room. Seriously, you're not deploying that stuff, or they're going to disable it right away. So we needed a tool that would actually allow us to do investigations without invading privacy, and without invading privacy of end users, but also privacy of data, user data we might be storing on databases, and we don't want the data to leave those databases. So let's do a few demos. They are recorded because I don't trust Wi-Fi, but if I have a little bit of time at the end, I will try to do some live demos. Meanwhile, let's the fox jump a bit. Okay. This is another one similar to the one I showed before, where oftentimes we find that private keys make their way on home directories, and we want to audit that because there are legitimate use cases for having private keys in your home directory, but they are rare. Most of the time, it's someone got careless for half a second and they created a private key and they started using it from a server and they forgot about it, and you have that private key that has access to a whole bunch of stuff. So what MIG does here, it's the same thing, calls the file module. Here we restrict the investigation to the agents that are tagged with the keyword OpSec. That's the name of, that was the previous name of our team. So the agents carry that tag so you can investigate them separately. You don't need to investigate the whole infrastructure all the time. You have filters you can apply to what you actually want to look at a given time. And we restrict the investigation to 30 seconds. I can't move this. Maybe that was a bad idea. And we look for a file that has a content private RSA key. So this runs on just 19 servers, and we'll just scan the home directories recursively, and you can pipe the output. So the good thing about the MIG command line is like it's all bash. You can pipe the output of your terminal to whatever tool you want. You don't need to go through a web interface or anything. You just do it, and you can script it if you want to. And it will return these 3 servers that have found private keys. Now, you have to continue the work manually. You have to actually go into these servers and look at these private keys and figure out if they're legitimate or not. But what's interesting here is that that server, external scan 1, I know for sure it's running in Linode. Oh yes, that's another one we have. And Linode is completely outside of any other network environment. It's not connected to any VPN or anything. So the MIG agent is actually reachable even if it's completely outside of your regular infrastructure. We have modules for inspecting network stuff. So the file module is kind of like find that you can call through MIG. The netstat module is kind of like netstat. It will read the content of procnet TCP, procnet UDP. It will look the content of the ARP tables. And you can do things like, is this IP currently connected to any of my systems? And that's very useful if you've seen an IP do bad stuff on one part of the infrastructure. And very quickly, you want to know if that IP is doing bad stuff on the other part of the infrastructure. Sometimes we'll see a user doing brute force in a specific website, and that same user is connected with a real username to another part of the infrastructure, so we can just tie the two together, and suddenly we have an email address we can use to continue flagging the user. So same ID, we distributed the investigation, and we found 2 servers, and those are even real host names. That was my home IP when I recorded this, and it was connected to a gateway host, a Bastion host. You can see that the JW1 has a connection on port 22, and ZLB6, which is a load balancer, has a connection on port 80. So that's a very easy way to just distribute an investigation across the entire network. Here's another one where a few months back we added a memory scanning module. So you can actually use MIG to scan the memory of your processes. And that is extremely useful if you got a report that there is a bad byte string that is currently exploding an Nginx or an Apache module, and you want to just take that byte string and run it across your infrastructure. Here, what I'm doing with this is calling the memory module, same thing on the OpSec host, and I want to scan Nginx only. I don't want to scan all of the processes. I want to just scan the processes that are named Nginx. That's a regex. And I want to scan for the content string tls.opsec.alizom.org, which is also a regex, and is actually the name of a virtual host. So, for example, if you've lost the server that is configured to serve a particular virtual host, you can use that technique. It's a very terrible way to detect a virtual host, but you could do it to find which server is configured to serve a given virtual host. But the main idea is you can inspect the memory of running processes without messing with them, because we're not actually taking a memory dump, we're not actually locking memory regions. it's completely painless to the servers. And it's fast, like all of these demos are real time. And once you have a tool that is low level like this, you can scan file systems, you can look at memory, you can look at IP addresses. There's a whole lot of things you can do with it. For example, here we're looking at USB device connected to a given system by just looking inside sys devices. So if you're looking for a specific USB device, you can do it this way. Locating a device by its MAC address. You've seen a device with a bad MAC address and you want to know where it is. Fine, just triangulate it by looking at all of the neighbors that see it. And that will tell you if the device is somewhere in an office, somewhere in your data centers, somewhere close to an access point. You can use that to, it's not super accurate, but it will give you a rough idea of where the device is. Particularly if you have a lot of VLANs, that will help you too. Yes?
Can you look at ARP tables?
You can look at ARP tables, yes. You can look at ARP tables. The netstat module is currently limited to macOS and Linux because I didn't take the time to add ARP tables lookup on Windows, but you can absolutely look at ARP tables. And for example, if you want to list troubleshooting, here is a troubleshooting example. If you want to list endpoints that cannot ping a specific destination because you have a problem with your firewall rules, or because you want to make sure that all of the systems in a given part of the infrastructure are behind a proxy, then you can use a ping module to just list all of the systems that can't ping a destination IP or cannot ping a destination IP. In this case, we have the flag -show not found, so we're interested in the system that did not manage to ping the destination IP. And the ping module supports TCP, UDP, and ICMP pings, so you can actually ping, for example, Google on port 80. If you do a lot of vulnerability management, it's sometimes very useful to have a clear inventory of your infrastructure and to know which system is running which service. But no one has that. No one knows for sure which servers are running Nginx or Elasticsearch or some random daemon. So using MIG, you can actually go look inside /proc and find all of these processes that are running Elasticsearch or anything else, Apache, Nginx, anything that matters at that point in time. That's just a clean way, and it's all real time, so you don't need to store that data. You can just retrieve it whenever you need it. Measuring security compliance. Is this large enough? Okay, so you guys can see this. Makes this bigger a bit on my side. What we want here is to make sure that SSH is configured correctly, that users are provisioned correctly on the systems, that the keys are set the right way, and all of that really boils down to looking into files. So if you have the right set of regexes, and if you have the right list of files, and you have listed what you want your systems to be configured like, you can just put all of that into a small JSON definition and run it across your infrastructure. So that's what we do, and we actually run that daily at Mozilla, and we graph it. And here what we're looking for is making sure SSHD config has log level verbose set, and that it has password authentication set to no. So at some point, we decided that it was time to have system security practices defined and have a list of stuff we want to find everywhere on all of the servers. And we're using MIG to verify that it's configured correctly. Now, if you have all of your systems puppetized correctly, this should never return a negative. Your system should always be configured the right way, and this will always have the right configuration parameters set, et cetera, et cetera. But it does happen that systems fall out of compliance. If you leave them online for like a year or two and Puppet broke, but it's a server no one looks at on a daily basis, you might actually miss it and it will fall out of compliance and no one will ever find it. And this is where doing regular testing, making sure you stay up to date, you stay up to compliance is good. We couldn't find a very good way to do that efficiently at the time of writing MIG. I know there are various efforts. SCAP, OpenSCAP is one of them. There are CIS benchmarks and all of these things, but actually running that efficiently across your infrastructure wasn't available. So MIG solves that problem. Another problem we're working on solving, is making vulnerability management better. And that's really one of the biggest issues we have right now, is making sure all of our packages are up to date. And when we get a new vulnerability, you might have heard or worked on even the Jenkins vulnerability that got released, and the new version got released yesterday. It's a pretty bad one. If you have a Jenkins instance that hasn't been patched, leave this talk now and go patch it. But if you have patched it, you might have run into the issue that you don't know where your Jenkins servers are. You don't know which version they're running. And this is where vulnerability management helps. You can write a definition, and Scribe is an extension to MIG. It's a language based on a JSON format that Aaron Mime wrote in my team. And it's a language that helps you describe an assertion on a package version. So for example, here, we want to make sure that libnss3, AMD64, because we care about Ubuntu here, has a version greater than 3.19.2. So the test here, the object tells us, look for the package name libnss3 AMD64. And underneath that, the test will say, well, when you have the object libnss3 package, apply a test to it and return a positive match if you found that the version is lower than 3.19.2. You can take that, and you can take the Ubuntu USN, Ubuntu security notices, or the Red Hat security advisories, or even better, you can take the data that is provided by the OpenVAST project in the NVT database, and take all that stuff and put it in a gigantic JSON document, a Scribe policy, and feed that to MIG and run it across your infrastructure in real time. I tested it again yesterday. I think the Red Hat document is 1.2 megabytes large, and the Ubuntu one is 800K. So it's not that big to distribute through your infrastructure, and it's not that long to run it. Each agent will take probably 1 or 2 seconds to run it, so the whole round trip will take between 15 to 30 seconds. And you can click that link and go look at some of the examples we have in the MIG repository of Scribe policies. You will see it's very long, and they're all broken down into grabbing the package and testing the version on that package. We have that problem solved for operating system packages. But the next challenge is being able to do that on stuff that is not in operating system package systems, like web frameworks, dependencies. How do you know that your Python web app has, I don't know, 100 requirements is up to date? How do you detect that this particular version of Django is not vulnerable? Same thing for Node.js or any other web framework. Well, the way we're solving this with Scribe is we're using MIG to retrieve the content of files on the file system, apply regexes to them to extract version numbers. So it needs to be catered to a requirement file to extract the right version number, and compare that with a list of vulnerabilities that we know. So it's not package management centric. We want to be able to apply that to pretty much anything that's represented in a file. And it's a work in progress, and hopefully we'll have something that we can run across Mozilla in the next few months. So if you've worked with security frameworks, and a lot of them have grown over the last few years, but they all have a flaw that they all love XML. I hate XML. There is no way I'm going to modify an XML document to make it do what I want. So when we wrote MIG, one of the goals was to be able to write these investigation files by hand. And this is one that, I don't know if I scroll here. Let's see. No, it doesn't. Okay. This is one that we wrote during the shell shock issue last year, that people started exploiting the shell shock vulnerability, and blog posts started publishing indicators of compromise. And I took all of these indicators of compromise and I put them in a MIG investigation. So let me try to find my... No, okay, fine. So what we see here is the whole JSON file that is actually sent to the MIG agents. You give it a name, so it's easy to find, and you give it a target. And in this case, we want to target all of Linux and Darwin systems And on the right, what we don't see is that it says mode daemon. So we just want the agents in daemon mode. Some agents like to run as cron job, what we call the check-in mode. So we didn't want to target those. And the file module here will search inside user bin, user sbin, bin, sbin, temp, and var temp for files that have one of those SHA-256 signatures. Underneath that, I have a few more indicators. We have some for, I don't know where my mouse is going. Never mind. We have some for byte strings inside of files, some file names, and then a whole bunch of IP addresses. And during the shell shock issue for probably an entire week, I used to run that every hour on the entire infrastructure because I wanted to make sure we didn't have one of those indicators that just hit us. And during that time, all of the ops teams were updating the system, making sure that they were patched, but we wanted to make sure that we were not getting owned during that process. A few extra goodies. This is more eye candy. It's when agents register to the platform, they give their public IP. We geolocate that with MaxMine. And in the MIG console, you can actually say, visualize the results on a pretty Google map, and it gives you something like this, where you can say, okay, I found agents in Asia and that's extremely useful if you're deploying MIG on end-user laptops and you don't know where they are. And that will let you locate them. So the point is, the faster we run investigation, the more we will investigate. And that really has become core to how we operate in the security team at Mozilla. We want to be able to run these things really, really quick all the time. Something comes up, we fire up MIG, we look, okay, we know within a minute that we're good, we're safe. And there are all sorts of examples where we want to use this. Someone leaves the company, we want to make sure that the accesses have been removed across the board. Library vulnerabilities, we want to find places where it's used. Finding IP addresses, somebody put his AWS key on pastebin, is it being used anywhere? Or sometimes we see something on a server, like a weird process running, we don't really know what it is, and 2 weeks later, something else comes up, and we're like, wait, what was that host again? And MIG can help you find that host again. So let's look at the internals a little bit. Go is a fantastic programming language. If you have not programmed in Go yet, try it out, because it's really good. I just went back a few weeks ago writing a whole client-side tool in Python that needs to support Python 2.6 to Python 3.4. I wanted to shoot myself. I swear. I made it, but I hated the whole process. I love Python. It's a great programming language if you're doing stuff server-side, but if you need to push your code to clients that run on I don't know how many different type of configurations, Go is much, much better because it all compiles to that one binary that will run anywhere. And the language itself is nice too. Static typing will catch most errors. If you're not a full-time developer, if you're not an expert in writing unit tests and all that stuff, Go will save you a whole bunch of times and catch errors for you. The way we deploy MIG is with the configuration, most of the time, with the configuration built in. So when we compile the MIG agent, we compile it with a number of configuration variables, and we try to keep these binaries, when we do keep these binaries private. If they leak, it's not the end of the world. It doesn't give access to anything. It's just the keys to register to the MIG service. But the benefit of that is that in some environments where we just find a server that is unmanaged, and it doesn't have any puppet, it doesn't have anything, we just want to put MIG agent on it and be done, then that way of deploying is very, very easy. We just copy the package, install it, and that's it. It needs to be secure. So the way we secure the infrastructure is by requiring that all actions that are sent to the MIG agent are signed using the PGP keys of the investigators that are kept on their local laptop. So when I send an investigation, my laptop will sign that JSON file, send it to the API, and it goes all the way down to the MIG agents. And the MIG agents will verify they know all of the public keys of the investigator that are authorized to run stuff, and they will verify that the signature is trusted. If someone owns the MIG platform in the middle, they don't have access to the keys. They can't send anything to the MIG agents. It would just be rejected. So that approach allows us to say the MIG infrastructure itself is not the most sensitive point of the infrastructure. It's not a single point of failure. We also have an ACL model where if you're operating in like highly sensitive environments and you want to make sure not a single person can run a whole bunch of stuff on your servers, you can use the MIG ACLs to say we want to, like investigators have a weight of 1, and running a module requires a weight of 2. So one investigator does not have enough weight to run that module. So you need to do cross signatures. Investigator A will sign your investigation, give it to investigator B that will review it, sign it as well. Suddenly you have 2 signatures. That's enough weight for the agents to accept it. So I think I removed my slide on the MIG agent module architecture itself, but basically we have a central MIG agent process and a whole bunch of modules that run external processes. And if you want to add functionalities to MIG, so for example, we don't retrieve raw data, we don't retrieve files. And sometimes for forensic type people, that's a problem because they want to have the files. Well, you could very well write a module and say, well, I wrote a module that will grab a file and publish it to an S3 bucket in AWS, for example. You could do that. It's a few lines of Go, or you can do pretty much anything you want. And writing that module is self-contained in that part of the MIG infrastructure where you don't need to know about anything else, and it's just a few lines of Go. It's not that difficult. Probably going to take you a day to write your first module and 3 hours to write the second one. So that's the overview of the MIG infrastructure. Check it out. We have an awesome domain name. That's a real thing. Check out the slides. I have stickers. If you want to come talk to me afterward, I can give you a cool little gator-looking MIG stickers, and I'm happy to answer any question.
Quick question. Since the MIG agent doesn't run as root, I've had instances.
It does.
Oh, it does run
Yes.
as root. I thought it did. Okay, I was wondering how you get to the var log messages and things like that if it didn't. So.
No, it does run as root. What we're looking at now is sandboxing the modules. So for example, the file module does not need to open network connections. So we have a team of students actually looking at using seccomp to lock down the activity of modules before they run. But yes, it needs to run as root.
Thank you.
And one thing I didn't mention is that we also have support for namespaces, so we can have better inspection of containers. So we're trying to build all of that into the core Linux module.
You should probably mention how many platforms we run this on.
Right now, it compiles on Linux, macOS, and Windows. We need to fix a few service initialization stuff on Windows. And I haven't tried, but I'm pretty sure it would be easy to compile it on BSD. And I'd love to have ARM support so we can do Android as well. And iOS would be nice.
Do we have any other questions?
Can you say a little bit more about the maturity of what you're able to do on the Windows platform?
About what exactly on Windows?
What can you do? How mature is it on Windows?
On Windows, okay. So all of the functionalities you'll find on other platforms are available on Windows too. The issue we have with Windows, since we have very few Windows servers at Mozilla, we didn't spend a lot of time working on the service initialization stuff. That should be fixed in the coming weeks, months. It's just a matter of paying attention to it, and we're doing that now. So you can do file investigations, you can do netstat investigation, the memory module works, the ping module works. So yeah, you can do pretty much all the other things you can do on Linux and Darwin.
With regard to searching for IOCs and other sorts of things, it seems like you never really want to retire an IOC. You want to keep on looking, right, in case it ever shows up. So does your list of things you look for just grow indefinitely at that point? Are you kind of replicating the functionality of something like an antivirus or a signature-based security product when you have that kind of approach? And you talked about, at first it was very ad hoc, but then at other points you've mentioned that you have these kind of daily scheduled scans as well. Does the list of things you're checking for daily just grow and grow and grow?
And that's kind of the antivirus problem. At some point your database is so big, you're just dealing with bloat. There are two answers to that. The first one is We do run a number of things regularly, and that list isn't that huge because a lot of these vulnerabilities target vulnerable versions of servers. So, for example, if you're attacking a Jenkins box and the Jenkins box is patched, do you really need to keep looking for that vector of attack in the future? For example, if it's a log line, if your IOC uses a string in a log line on a PHP app, like a WordPress app, and you know that's been fixed, you can remove it. But there's a number of things we want to be running regularly. Rootkits and all things like that, we run it regularly, rootkit detection. So there are really two parts. The first part is your IOC tied to a particular point-in-time event kind of attack? And if that's the case, how long are you going to scan for it? And then you can remove it from your pool. So you can prune it a little bit. And the other part is being able to run these things regularly in a fast way. And the way the file module is designed today, it will only do one pass on your file system. And it will only look at a file once, and then compare that checksum from the file across all of the signatures you've given it. So you can actually keep adding to one investigation and run it as one item, and it will have the same cost that it will have if you're looking for one checksum and if you're looking for 10,000 checksums. You do want to make sure, though, that you're not running anything that's going to take down the servers. And the MIG agent, by default, will time out module investigation after X number of seconds. And right now, I believe it's configured to 300 seconds. So after 5 minutes, the agent will kill the module and return the timeout to the platform saying, it ran for too long, I want to be nice to Amy, otherwise she's going to yell at me because I'm using all of our CPU resources, so I just killed it.
Is there anything special you do to make sure that the agent is running everywhere across your platform? It sounds like a pretty big distributed platform. Is there any tricks you have to keep it healthy?
There's a couple of things in the agent itself that are kind of brute force approach to things, like it will have its own watchdog, cron job, and if the agent, like when the agent starts for the first time, it will just create a cron job and check for itself every 10 minutes, and if the agent process isn't running, it will restart itself. That works well, and that allows us to crash the entire MIG, because RabbitMQ can be a pain in the butt, and it will crash sometimes, and you just disconnected all of your agents. You don't want to go one by one on your servers and restart them, so that cron job will just regularly restart the agents, and the agents will crash themselves when they lose RabbitMQ connectivity. We do use a little bit of other monitoring, like standard monitoring tools. Like there's still some Nagios. I think that's pretty much only on Nagios. And another thing you can do is that since all the agents register themselves, you can actually put a report every week saying which agents have disconnected and not come back, and which ones are the new agents that just got added this week. And that's a manual process, but it gives you a report of, okay, this has changed, and then you can compare that manually with normal activity in the infrastructure. It's still, there are different parts of the infrastructure at Mozilla. Some parts are fairly static, so it's easy to go through that list. And one part is very, very dynamic, which is all of these spot instances that just rotate daily, and you have 5,000 of them rotating daily. We just accept the fact that we might miss a few there because there's just no way to audit all of them.
Yeah, for those are actually spot instances, and we often shut them down after several hours to spin up new spot instances. So they're really short-lived. Any other questions? All right, thank you, Julien.